Alright, so far in the course we've learned about elements and their charges, and of course that's what governs opposite charges to attract from one element to another, and when they combine they form a compound. So we learned how to form those compounds in the correct ratio so that we could write the correct formula, and then we learned how to name those compounds. Well, this particular chapter takes that one step further and allows us to draw the structure of that particular compound and then determine what the shape or geometry is when we look at it three-dimensionally. So it basically makes things come full circle. The method that we use to draw these compounds is called the Lewis dot method, and as the name would indicate, we do indeed use a dot structure to draw the electrons and how they are distributed within the elements and the compound itself. So basically it is just a series of dots and solid lines, whereby the solid lines are just connected dots. So what we really have is electrons written as dots, typically in a pair, so that we have what we call a pair of electrons, as you can see here. And when they are in pairs as dots, that means those electrons are of course a pair of electrons, but they are in a non-bonded state. So therefore we call them non-bonded or lone pairs of electrons. If those electrons are involved in a bond, we actually connect the dots and we write that as a pair of electrons that are in a bonded state, or bonded electrons. Now of course what that line means is two dots, two electrons. So every time you see a line or a hashtag like that, that represents a bond, and that also represents two electrons. So the steps in how we draw a Lewis structure are basically listed for you as follows, and they may look quite intimidating at the beginning, but once you begin to practice, you can maybe combine these rules, or they will come second nature to you. There is one video tutorial here which reviews the rules and the following examples, and I will list yet another tutorial that is this particular one where I'm actually drawing the structures with you, so it's a little bit more of a detailed or hands-on explanation. So what you're basically going to do is, in order to draw a compound and therefore a structure, the entire infrastructure of a compound is based on these electrons, as if the electrons are the glue that holds the different elements together. So just as you're building a home, let's say, or some sort of a structure, you will actually then need to take parts of that structure and put them together. And in order to do that, you need electrons, almost as a form of currency. So how do we know the total number of electrons that we have at our disposal to build this, quote, compound? Well, the first thing we're going to do is count the total number of valence electrons. So valence electrons are basically electrons in the outer shell. They're the same as the group number. So let's say you've got an element from group 3, it would have 3 valence electrons. From group 7, it would have 7, and so forth. So you will count the total number of valence electrons of every single element that you have in your given compound, and literally put it in, let's say, a little bank somewhere here. Next, of course, is to look to see if there are any charges on the compound. If there's a positive charge on the compound, that means you've lost electrons. You need to subtract the total number of electrons that correspond to that charge from your electron bank. If there's a negative charge, then you'll add those, because that means electrons have been gained. The next thing to do is, now that you have, say, electron capital, almost like it's currency to build your structure, you're going to build the foundation of your structure, just as you would build the foundation and the skeleton of a home. So we're going to build a skeletal structure simply by attaching all the elements to the central atom. That's our first step. So typically the central atom is the compound that is listed, the element that's listed first, or the element in which we only have one, and that will be in the center, and then all other elements will be attached to it, similar to this. So this is what we call drawing a skeletal structure, just getting what the basic outline of the compound looks like. In order to do that, of course, we're setting up some bonds so that, the central atom X is bonded to element Y, such as this. In order to have these bonds, of course, that comes at a cost. And each one of these bonds, remember, corresponds to 2 electrons. So for each bond that you form, you should be subtracting 2 electrons from your, quote, bank. This is very important to remember. Next, you're going to then satisfy the octet of all the surrounding elements. That means the Y's here. All of these, you need to satisfy their octets, which means that each element typically wants 8 valence electrons to be stable. That's the octet. So at this point, every bond you've given represents 2 electrons. So in the case of this example, you need 6 more electrons to fulfill the octet. Now we say most elements, almost all. The 2 most notable exceptions are hydrogen and helium, and because they're very small and have only an s subshell, then they will only want 2 electrons. So they don't want 8, but rather 2. One bond, for example, to a hydrogen would satisfy its 2 electron maximum. There's no need for an octet. So basically what we're going to do is, in this example, we need to give this Y element 6 additional electrons because there's 2 here from this bond and it needs 6 more to make 8. How do we give them? We give them in the form of pairs of dots. There's 2 and there's another 2 and another 2. That's 2, 4, 6 dots, 3 pairs, 6 lone electrons, 3 lone pairs of electrons, and another 2 from this bond. That gives you 8. We'll do 6 here, 6 here, 6 here, 6 here, 6 here, and then of course they'll have 8 valence electrons for each one. That is, of course, if you have enough electrons to do that, which hopefully you will. The next, of course, is to look within the atom, within the central atom itself, and to satisfy its octet. Hopefully you have enough electrons in your bank, or sometimes, as in the case of this example, you already have 8 because of the number of bonds that you've set up with your skeletal structure. There's 1 bond, 2 bonds, 3 bonds, 4 bonds. Each bond, again, is at a cost of 2 electrons or worth 2 electrons. That means this X element already has 4 bonds or 8 electrons. It already has an octet. So, the whole goal of this is to first find your total electron tally and then distribute it. First, you will distribute it to your surrounding atoms, then to your central atom. And the whole purpose here is to form an octet. Distribute to 8 electrons. And that is all within the confines of this electron tally. You have to use up the entire electron bank, but not exceed it. That means that if you have 20 electrons in your tally, you need to use up all 20 electrons, but no more. No more and no less. And that is the caveat. So, again, recall that you've got to use all electrons in your bank, but no more. And most of the time this works out quite nicely. You will have satisfied the octet of all elements with the number of electrons that you have, and there are times, however, you will actually not be able to do that because you will run out of electrons. And when you run out of electrons and you cannot fulfill the octet, this typically happens to the central atom because it basically gets looked at last. So by the time you get to the central atom, everybody else on the surrounding areas has a full octet, but when you get to the central atom, you've depleted your electron stores. This is the point at which we start to form multiple bonds. Multiple bonds, such as double bonds or triple bonds. They represent, of course, 2 pairs of electrons being shared, which means 4 electrons total. And 1, 2, 3 bonds, a triple bond, represents 3 pairs of electrons, which is 6 electrons total. The whole premise behind forming a multiple bond is when you run out of electrons, you can just simply have them share more than 1 pair. This allows you to satisfy the octet of several atoms with the same number of electrons, almost economizing your electrons or stretching your electron dollar. But multiple bonds are not favorable to form because they're very high in energy. And the whole premise is that we're trying to draw the most stable structure. So multiple bonds should not be drawn at random. And they're not very often seen. They're only used when necessary, when you run out and when you have no other alternative. That means your choices would be A, to leave the central atom with no octet because you've run out of electrons, highly unstable, or B, to form multiple bonds, meaning take some of these outer electrons and share them, making a double bond and losing those, in which case that is also unstable. But which is the lesser of those two evils? Forming of the multiple bond. It's much better to form a multiple bond and satisfy the octet of a central atom than to leave it without an octet. Neither is an ideal scenario, but the latter is at least more favorable than leaving it without an octet. Last of all, if you do have any kind of charge from step 1 that you observed, make sure that you indicate it in your final structure by putting a bracket and a positive or negative sign, whatever the charge happened to be. And so if you take a look here at your examples, they go on to put all of these rules into practice. And the more you practice these problems, the more different scenarios you'll encounter and the better off you'll be in terms of how well you can draw these structures. So here, if you such as carbon tetrachloride, CCl4, ammonium, which gives you a cation example, carbon dioxide, which gives you an example of multiple bonds being formed, and also an example here of where you need to apply lone pairs to the central atom. So it's not always the outer elements that get electrons. Sometimes nothing gets any electrons and the octet is still formed. Sometimes we run out of electrons and sometimes we have extra electrons. So these 4 examples really do go through almost every possible scenario, and they definitely help you to understand better how to solve these or how to draw these structures rather. So let's take a quick look at a couple of these, beginning with carbon tetrachloride. You have carbon here and 4 chlorine. So carbon, because it's in group 4, will have 4 electrons donated to the bank. Chlorine, being in group 7, will give you 7 valence electrons. Since we have 4 of them, that's a total of 28 electrons in our bank. 28 plus 4 is a total of 32 electrons, which must be used. All of them have to be used, but no more can be used. So carbon is in the center. Why? Because it's listed first, and it makes sense that it would be in the center since there's only one of them, and the 4 chlorines can then surround it. So carbon in the middle, put a chlorine on either side, and attach each chlorine with a bond. That's 4 bonds. 4 lines, which each represent 2 electrons. Remember, that line is a bond that represents 2 electrons. So we have 4 of them. That's 8 electrons that are lost. So from these 32, we lose 8. That leaves us with a total of 24 electrons. So we look at this chlorine right now with 1 bond. That's 2 electrons. It needs to have 8. If it already has 2 and it needs 8, that means we need to provide it with 6 more electrons in the form of lone pairs. So 6 electrons means 3 pairs. There's 1 pair and 2 pairs and 3 pairs. And each chlorine is in the same position. That means they each need to be given 6 electrons in the form of 3 pairs. 2, 4, 6, and then this right here gives it 8. 2, 4, 6, and this gives it 8, and so on and so forth. So 6 here, 6 here, 6 here, and 6 here. That's the 24, and there is 24. All right. So we reached the goal of using up all 32 electrons, but is that going to basically be problematic once we look at the central atom? Let's take a look here. We have no electrons left, and we still have not looked at the central atom. We need to satisfy the octet of the central atom, and yet we have no electrons left. Hopefully, the octet would have already been satisfied with the bonds we formed in step 1 with the skeletal structure. But if not, we'll have to form multiple bonds. Let's take a look at carbon here. Carbon has 1, 2, 3, 4 bonds. Each line again is 2 electrons times 4 gives you 8. So this carbon indeed has 8 electrons and it has an octet. Luckily, since we have no electrons left to give it. No charges, nothing to add or subtract, no brackets needed, and this structure is drawn to perfection. Speaking of charges, let's take a look at ammonium here, NH4+. Nitrogen being in group 5 gives us 5 valence electrons. Hydrogen being in group 1 gives us each 1 valence electron. That's a total of 4 electrons from the hydrogens, 4 times 1 apiece. That's a total of 9 electrons, but notice this positive charge. That means electrons were lost. How many? It's a +1. That means 1 electron was lost. So we subtract 1 electron from the tally, and that gives us our actual true value. 8 electrons are what we really have to spend here. Again, put nitrogen in the middle, flanked on either side by the 4 hydrogens, and that means the basic skeletal structure has 1, 2, 3, 4 bonds at a cost of 2 electrons each. That's 8 electrons used just by building the skeletal structure. That is all of our electrons, and we're already left with none. That may prove to be problematic and maybe not. Let's take a look and see. By building the skeletal structure, at least we have established the foundation of our compound, but that has also left us with no electrons in the bank. Alright, let's take a look and resume our steps. Outer atoms are hydrogens, which means they only want 2 electrons, not the 8 from the other octets that we've been looking at. That's one of our exceptions. Hydrogen only wants 2. Notice how it already has 2, just from that bond. 2 electrons. 2 electrons. Remember, these bonds represent 2 electrons that are being shared. That means both nitrogen and hydrogen can claim ownership of them. And all they represent is that these 2 are actually bonded together, or these 2 electrons are attached. That's what that line means. So what that means is that each of these hydrogens already has 2 electrons, and its, quote, revised octet of 2 electrons has been satisfied. Great, because we have no electrons left to give it. Now we've passed one hurdle, but we're not done, because look at this nitrogen. We still haven't looked at that. Does that have an octet? Let's take a look. Nitrogen is in the center. It has got 1 bond, 2, 3, and 4. 4 bonds times 2 electrons apiece. Yes, it does have an octet, and we didn't have to do anything to achieve it more than build a skeletal structure. Good thing, because again, we had no electrons left in the bank. So, indeed, we did draw our skeletal structure and fulfill the octet all in one step and used up all 8 of our electrons, no more and no less. Last step, of course, is to provide this bracket and put the +1 charge at the outside so that, of course, we can indeed have a way of determining why only 8 electrons were built in the structure, because of this positive charge, and that helps us to basically confirm why we used 8 electrons. Let's continue on with a use of a double bond here in carbon dioxide and lone pairs on the central atom, since we have not yet seen that. We've seen it on the outside but not on the inside. And then we'll take that one step further in determining what these structures would look like 3-dimensionally when we look for our geometry table. So that will be in part 2 of this tutorial.